My name is Anna Hoffman. I'm a data and applied scientist on the Azure SQL engineering team at Microsoft. You might have seen me. I was wearing a much larger SQL Server 2019 t-shirt this morning on stage with Rohan. But today we're going to talk a little bit about something different. And someone came up earlier and said, is this going to be more on-prem or more Azure? And this is more of a generic talk. Talking about AI and ML and deep learning. And the examples I do will be split between on-prem and Azure, and even just not even related to SQL at all. As we get started, I wanted to bring up, it'd help if this was on. I wanted to bring up this learning pathway. How many of you knew this was part of a learning pathway? Awesome. How many of you went to Melody's session before this? Awesome. Great. Cool. So for those of you that didn't, that's OK. But we're here. So we're in a behind-the-scenes look at machine learning, AI, and deep learning. And we kind of thought about this pathway a long time ago, back in March. And we said, how can we have a pathway for AI? And we were originally just going to have like 4 or 5 sessions that went straight down. And then we decided that for many people, AI is going to mean different things based on their role. So that's kind of why you see it kind of forking out. Now you could, in theory, go to AI sessions all day tomorrow. So if you look, I think they're all. No, there's one on Friday. So you can go to 3 sessions tomorrow and 1 on Friday. And so the purpose of this session, then, is to kind of give you a behind-the-scenes look at what's happening. So when you start using AI, or you start using machine learning, or even using deep learning in your applications that you build, you have an idea of what's going on behind the scenes. You don't necessarily need this idea, but understanding how things work can be helpful. And also, at your next holiday party, you can say that you know AI, ML, and data science now, and deep learning, and be really smart and basically put it on your resume. And you're going to be a genius after that. So everyone's excited. Like after this, you're all data scientists. And you get a pay raise. Yeah. Bob and I did a session earlier today, and he said, you put containers in the title of a talk, and people come. But I think AI might be one of those topics, too. So thank you all for coming with me and hanging out today. I know Bob is doing a session at this time, too. So it's nice that you chose me over Bob. I'm sure his room's packed. But anyway, so we're going to talk about data science. Then we'll go into AI, machine learning, deep learning, and then some of the tools and how it relates to your day-to-day job, and then where you can go after this for more info. And I haven't put my latest deck up online yet, but it is on GitHub, and I will put it online later today. So don't worry about that. OK, so let's start by talking about data science. Now, this first part, the data analysis part of data science, is something I think probably everyone in the room is really familiar with and really comfortable with, right? So your programming and control, reporting, your BI, even some of the data mining stuff that I'm sure a lot of you are doing comes in the data analysis side. Then the science side is really about the scientific process. And we came up with something called the team data science process. Just a quick glimpse at that. If you are looking, that's not the right tab. If you are looking to get more into this after, this can be a great tool for learning and also having data science projects. So you see there's like several phases here. Actually, I blew this up. In the data science lifecycle. And we won't run through all of these exactly today, but if you go to this page, then there's a ton more resources on how you can actually go about implementing this project with your team in your company, as opposed to just like going and creating a model. OK. And then in data science, there are these topics like artificial intelligence, machine learning, and deep learning, which you've been hearing a lot about. So I wanted to do like a very short history lesson, and it's very short, I promise. But basically, in the 1950s, we started having this idea of artificial intelligence. And a big reason for that is because some folks were like, oh, we can predict how humans act. They are very predictable, a number of if-then statements, and we can pretty much program a human however. For example, a kid goes to a birthday party. He's going for the pizza, not the salad, right? So we can predict humans. It turns out we couldn't actually predict them that well in a lot of scenarios, and we didn't quite have the computing power or the data infrastructure to do the analysis that we needed at scale. So it kind of died off a little bit, and then later in the 80s, machine learning, but maybe not called machine learning, more of statistical modeling and data mining became very popular. And only more recently, in the 2000s and the 2010s, now that we have this massive infrastructure to be able to deal with compute and to deal with all the data that we're processing, have we gotten into deep learning. Now, the reason for this is machine learning typically, and of course it all depends, but typically will converge after it receives a certain amount of data. But with deep learning, the more data you give it, the better it can get. So we can start to answer more complex problems when we have more data. So we'll talk about that today. OK, now I kind of talked about artificial intelligence. So artificial intelligence is more like a broad category that just means anything that can mimic human behavior, typically using math. And so as I was mentioning, in the 50s, they thought that it could be so precisely described that we can simulate it. And so we started with things that are what I'll call symbolic, so logic systems, if-then systems, so your expert systems, some simulation, so if you've played with the Arena tool or any simulations, less of the statistics that we got into later, starting in the 1980s. OK, now if we think about kind of the categories in artificial intelligence, there are 5 main ones, and they're here. These aren't all of them. These are just a lot of the ones that we see for mimicking human types of behavior: decision, language, vision, search, those sort of things. These coincidentally also happen to all be cognitive services, which I think most of you have probably heard of. They're basically machine learning models that Microsoft Research has been working on for years. And we've put them available to you to use as APIs. So you can make REST calls and get results on your images, on your data, et cetera. So I just wanted to show a quick demo of how this might play out in SQL. And I want to be clear here, this could be SQL on-prem or SQL in Azure, or SQL, or just some data system somewhere else. Let's switch it back. OK, and the other thing I'll say is I'm not going to go through all of the code. All the code is not showing on screen. But I have instructions on how to do this in your environment, and then some all on my GitHub, which I'll share at the end. OK, so this was something I played with when I first started working on SQL. I've been in the AI engineering team the past few years before I came here. So I'd been working with cognitive services a lot, and I said, I think we could use these here. So here what I'm in is Sql Server 2019, which has support for Java. But really, you could use any of the things that are built in SQL today to do this as well, because we're just making REST calls. So you could use R, Python. You could even use CLR. OK, so what I did is basically I just looked at some product reviews. You see product ID, product review. And I created this Java program called sentiment.jar. And it basically calls the cognitive service, the sentiment analysis one, and returns the result. Pretty simple, pretty easy to write. I basically took the sample code from the docs for this cognitive service. So now I can use an external script to actually execute that program on those reviews you just saw. And we get sentiment scores back. So pretty easy way to start taking advantage of this immediately, and a good idea of what AI might mean. Now, I took this one step further, and we have some cognitive services that are custom. One of the several examples is LUIS, which is natural language understanding. So if we take another example, and again, we're just staying high level here. If we take another example and say, I have delivery instructions. And these come in as raw text into my SQL database. And I want to be able to parse out information from these. So what I was able to do is create a Lewis model, and it's all done through a GUI. It's very easy to do. It's very intuitive. And put it into this Java program again. And by calling it, I was able to parse out things like the origin, the destination, and the delivery date time. So this is just a pretty easy example of how you can start taking advantage of this today and leveraging the SQL technology we have today. So for example, this was done in SQL Server 2019, but I was making calls out to the cognitive services which are hosted on the internet. So that could be a problem. So cognitive services, just a short aside, are also available in containers. So when you hear about big data clusters and things like Azure Arc, I can actually deploy my cognitive services containers into my big data cluster or into my Azure Arc service and then really scale this as well. So if you had a lot of data that you were processing. OK, so just one example of artificial intelligence that you don't really have to work too hard to start taking advantage of. These are all the cognitive services that are available today. So that's kind of what I refer to as applied AI. And I think some of the sessions that are later in this pathway will go into that more as well, how you can really start taking advantage of these models that we've been working on for years today. OK, so now we get into machine learning, which is a little bit more specific than just artificial intelligence. It's a specific way of doing things. This is the formal definition. So a computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance in, OK, like my eyes have glazed over, like I'm done with this, right? OK, so let's think about it a different way. And I'm just going to animate a few of these. OK, so let's say I have a bunch of images. And some of them are cups, and some of them are not cups. And I want to identify which ones are cups. So I have the image, and then I have features. Now, this is a term data science people use, which is basically just columns that can be used to predict the result you're trying to predict. And we call those labels. So we have our features, and we have our labels. So after analyzing the features, there's a label that we've assigned it to, is it a cup or not, basically true or false. So what a machine learning model will do is take in all this data and try to create some sort of model. So in this case, basically, if it's got an open top, it's got a closed bottom, it holds liquid, and it's hand size, then it's a cup. So pretty simple. So it'll see this, and it'll run through that model and say, yeah, it's a cup. And it'll give you some sort of certainty or confidence or accuracy. And we can get further into that later. So that's kind of your basic idea of how machine learning works. It takes in data you give it, and then is able to iterate through and determine what labels can be. And this is an example of supervised learning because we know what the answer is. So it's basically supervised because we're able to give it the right answer. And now unsupervised learning is where we don't really have a right answer to tell it, and we just want it to infer, so like create groups or find anomalies. So there are 5 main algorithm families for machine learning. And one is regression, so how much or how many. You've seen this a lot with forecasting. Is it odd? So is it an anomaly? So in something like a factory, are we getting some error that might signal something's wrong? Which category? So this is classification. And this could be supervised. So we could have a classification we want to give it. Or it could be unsupervised. We have which action, which is more of like a reinforcement learning type of thing. And then we can also put things into groups with recommendation systems and clustering. OK, there are a lot of languages that are available for machine learning. I think that R and Python and then things like PySpark are the most popular. But there are ways of doing machine learning in Java. I'm not sure really anyone does. This is some example code in R. Basically, what's happening, if you look at any one line, you're training a model, and then that first input is going to be what you want to predict. So this is the iris data set. It's very popular among learning machine learning. It's basically a bunch of different flowers, and you try to predict what they are. But so we have the species of flower, and then you specify the data you want to train with, and then you can specify some other things. And this is in R. I have an example, and again, all the examples I show I also have on GitHub, so you can actually walk through them. But I have an example around wine quality. This is another pretty famous data set. And there are a lot of free data sets from here, which you'll have access to this, that you can access and learn from. But what I've done is I'm leveraging in-database machine learning, which is kind of similar to what we do with Java. In this case, I'm using Python. So what Sql does, and Python started being supported in Sql Server 2017, what Python does is Sql Server is basically able to launch. We actually call it the launch pad. So we use the launch pad to launch satellites that can run other languages programs, so R, Python, and now Java in 2019. So I'm using in-database machine learning here. And I'm also using RevoScale Pi. Microsoft acquired a company called Revolution Analytics, and they made these libraries that can do distributed machine learning. So we've actually taken in those packages. They're proprietary, but you can use them in things like machine learning services here. But basically, all I do is I get connected to my Sql server, and then I can set the compute context to SQL. So that means I can leverage the compute in my SQL server, or I could leverage compute somewhere else. Now, again, and I'm not going to go through all of these, but I can start to do things like look at the data. So here I'm doing SQL queries in Python through SQL, which is a little funny, but I can start looking at the data. I can start doing things with packages like matplotlib, which is a very famous Python package. And I can start to look at the data. So here I'm trying to look at the distribution of red and white wines and how their quality might be different among colors. I don't really see any huge patterns there, just that there are a lot of really mediocre wines around. And then what I'm going to do, so we get our data, we do some sort of data engineering. This is really the big part, the data engineering, getting the data ready. All those data scientists who say that they have the hard part, it's not true. It's like all the people doing all the stuff before the data science part, right? I just say use this model from scikit-learn. But what we're going to do is we're going to split the data. So I'm going to split it into my training and my testing data set. Sometimes you might also have a validation data set, but basically the purpose of this is you want to train on one set of data and then see how it performs on a set of data it hasn't seen before. If we use the same data, it's called overfitting. We'd likely overfit our model because it's only seen a specific number of things, so it's kind of just fitting very tightly to the data that you have. So when you show it something new, it doesn't really know if it hasn't seen it before. So we'll split our data, and once we have our data split, we can create a model. So here I'm leveraging one of the Microsoft ML packages, RxFastTrees, and I'm saying I want to be able to predict the quality based on the columns in the data set. I want to use the regression mode, and I want to use the compute context of in Sql Server. And it basically creates this model for me. It trains, and then I can take a look at some of my predictions. So this quality is the actual quality, and this score is what my model predicted. And this is pretty good after just training over a few thousand data pieces. And again, I won't go too far into this. Now, once you have a model, just to throw in some more SQL stuff, once you have a model, you can use a program called Sql Ml Utils. This is an open source package we developed for Python and for R. And what this does is it can take your Python code or your R code and actually turn it into a stored procedure that will run in your SQL Server instance. So if you're me and your DBA says, no way, you cannot have access to that SQL Server, you can still leverage this to create a stored procedure. So basically, you can create a stored procedure from a function, and then within SQL, you can do things like adding it to the predict capabilities. So you can basically serialize your model within SQL Server. Okay, so that's kind of an example of machine learning. Again, very quick example. We're going very fast. Definitely didn't get all of this, but it's all available, and hopefully some of it's sinking in. Okay, so let's talk about deep learning. Okay, so with machine learning, I can learn to predict that this is a dog, right? If I give it enough images, it will probably be able to recognize a dog that's also standing up, but it would need lots more data for that. Okay, so we were in South Africa a few months ago, and we went on a little mini safari. And anyone see a dog? So it's hard for us to see a dog here. So it's probably going to be a lot harder for just a regular machine learning model to find the dog. It was very hard for us to find these dogs. We drove around for a long time looking for them. But anyways, it gets very hard for a model to recognize things like this. And that's when deep learning can really help, right? So in the next few slides, we'll kind of walk through what deep learning is, how it works, and hopefully the math won't glaze your eyes over. But time will tell. Okay, so we'll keep this very basic. So if you already know things about this, I'm sorry, but I'm going to try to go very slowly so that we get it. So if we think about the components in a deep learning model, you've probably seen something like this before. The first component on the left is the inputs. So this is just your raw data. So if it's a picture in the form of numbers. And what we do is we basically take each value. So if you think about the cup examples, we had different features. Now, in something like an image, we're going to have a lot of features, right? Because every single pixel is going to be represented by a number. And if it's a colored pixel, you're going to have basically layers of the colors that go into that. So there's a lot of things there just in itself. And this forms the input layer. And each of those is going to have like a node. That's what we call those little circles, like a node. Okay, now we're going to take that and do some math on it, which we'll get to, into a certain number of hidden layers. There could be 1, there could be 50. And the connection between these layers can change, but for the purposes here, we're basically just saying, okay, every node will then go to every node in the next hidden layer, and then we'll go to every node in the next hidden layer, and so on and so forth, to get to an output layer. And then your output is kind of like your answer. So if you were trying to predict a number between 0 and 9 that was handwritten, your output would be 10 values with a confidence for each value. So if you had a confidence of 0.8 in the last value, that would mean pretty high chance this neural network thinks it's a 9. Does that make sense? Okay. And that's how you get your outputs. Okay, so now let's take a look at what happens in one of those nodes. Okay, I heard a involuntary reaction from someone. Oh. Anyway, so who remembers the equation for a line? Yes. Yes. So y equals mx plus b is like your standard equation for a line, like a linear function. Okay, so that's kind of what we're doing here. So if you see in that one node, I put the plus b because it's actually there. It's called bias. Nobody puts it in these graphs because think of every node also had a b. They would look very ugly very quickly. So we don't put that there, but basically for every input, so for every node coming into another node, so if it's the input or if it's some layer in the middle, we're going to take that and multiply it by a weight. So each of one of these circles that you see, except the last one, the output layer, is associated with a weight and a b, a bias, okay? And so what we're going to do then is we're going to sum all of those together that come in, right? Because like if we look at the first hidden layer, there are three nodes coming into that, right? So So we're going to have 3 mx, 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 so we'll sum those. Okay? We take that sum, and then we do what's called an activation function, because we don't actually want this to be linear. And what this activation function does is it's supposed to be like, should we fire the neuron or not? Okay? So this equation, this is called a sigmoid. Don't worry too much about it. What I want you to notice is that on either side, we're either at 0 or 1, right? Basically, if you put in a 3, you're going to get 1. If you put in anything negative, you're going to get very close to 0. Following still? So this basically takes in a number and says 1 or 0. So think of it like a switch. It's saying we switch that node on or off, basically. OK, so that's how we get the output. So that would be, if you look at the hidden layer at the top circle, that would be 1. So now we do that for all the ones in the hidden layer. And then depending on how many hidden layers they are, we do that again, OK? So we'll go through summing the mx's, adding the bias, going through the activation function, going to the next one. So if you think of one coming out, I guess it's hard for me to point on here. If you think about a value coming out of the hidden layer top circle, that value will then be multiplied by the weight that we've assigned to that value, and then summed down with all the other nodes coming into it to go into that output layer. OK, then we do our sigmoid, and we turn it on or off. OK, this process is called feed forward. OK, so we're traversing this way through our neural network. OK, now once we've done that, we want to understand how wrong we were. So if we take it from the top, and I apologize if I'm simplifying too much, but if we take it from the top, I'm going to explain this loss function. So what we're saying is take the actual minus minus our prediction, and then square that, and then sum them among all the values. So we get this loss, and then what we want to know is how is loss changing. And the reason we want to know that is we want to know, are we getting closer or further away from the right answer? And there's a lot of math in there. You can see I didn't even put it all in there because there's just a lot of math. We go into chain rules, if you remember calculus, and we go into derivatives. But really, what we're getting at is how is the loss changing? Because if you remember, derivative is just the slope or how something is changing. So what we want to understand is how is the loss changing? And is it changing so that we can get closer to decreasing our loss or coming to a minimum with our loss? OK, so what we do then is we update our weights to be the old weights plus the derivative of the loss. So if we were changing in the right way, we'll go closer to that. And if we're changing in the wrong way, we go the other direction. OK, and the way we do that is backwards. So we go back through this way, the model. So the way this works is we feed forward. So we go through the neural network to your right, and then we go back. OK, so at each node, we're calculating some of the loss, derivative of the loss, and updating those weights. Now we have our new weights, and we go back. Following? And we'll do this like thousands of times, or hundreds of times. And then hopefully, we'll have a good idea of what these weights should be. And so you can see how the amount of compute required for these sort of things, especially when you're dealing with a lot of data, is very important. OK, and then we'll go again. OK, so now let's think about a different example. Now, this example is much more complicated because what we might be trying to do is facial recognition. So we have to identify that there's a face in this picture, and then we have to identify who is the face. So for something like this, we need a lot of layers. And like I kind of mentioned earlier, this is even simplified because this image is black and white. So we just have one layer of colors to look at. But over many iterations of the feed forward and the back propagation, some of these layers might start to look like features. And just a reminder on what features are For the cup example, a feature was, does it have an open top, a closed bottom, does it hold liquid, is it hand-sized? Okay, so we can start to do that with images of people. So you can see we're able to identify edges, and then we can say, okay, well, some of these combinations of edges might be parts of a face, like an eye or a nose or a mouth or et cetera. And then we might have a layer that actually has object models of those faces. And now the crazy part is, like, we don't really look at each of these layers. We're kind of looking at the combinations of them as a whole. But this is kind of the power that deep learning is capable of, something that would be very hard for me to sit down with a piece of paper and try to figure out how to math that a face is a certain person. So you might be wondering, how do we turn these images into numbers? Some of you might have worked with images before, so this will be review. But if we take, like, the number 8, for example, this is a very famous data set. There's a bunch of handwritten digits, and if you pursue this further, I highly recommend playing with this data set and trying to create a model that can recognize handwritten digits. But anyways, what we're doing here is we're taking an image, and it's very common to try to break an image down into a 28 by 28 pixel image. I don't know why, but that puts you, if you do 28 times 28, that's 784. So basically think of all of these numbers being one row, so all features. Every single one of these numbers is a feature. So when we saw the cup and we had 4 features, now we have 784 features for one image. So that can be a lot of data. And you can see basically here it's 0 everywhere that it's black, and then it's some variation between that depending if it's kind of like, you know, part of the 8 that's just kind of half the 8 or whatever. And now what you'll see is we take every single one of those pixels, and that becomes our inputs into our neural network. And we can have lots of layers, lots of nodes. We can also do different activation functions. So there are other, we saw the sigmoid, but there are other things, other functions besides sigmoids. People with me still? You with me? Okay, all right. Okay, well, let's see if I can break you. Okay, no, I'm just kidding. I don't want to break you. If I lose you, please, like, stop me, and we can try to talk about it. Okay, so if you want to follow along, I don't see anyone with a laptop, but if you want to follow along, there is a pre-run Jupyter notebook here that you can look at as we look at it, or you can just look at it now, and then you can look at it on your own later. But just know that it's all there. Okay, so I didn't say this before, but this is Azure Data Studio. Any of you seen this before? I love it because coming from an AI space, like, Jupyter notebooks are really important for data science because you can mix your markdown and instructions with code. And now the great thing about Jupyter notebooks is that you have SQL notebooks, so you can do the same thing with SQL. But here I'm just connected to Python locally. And I definitely recommend, like, walking through this example yourself and trying to understand all of the things that we're doing. Okay, so the first thing I did is I imported NumPy as NP. This is a very common thing to do. How many people are, like, pretty familiar with Python? Just so I know. Okay. Okay, so NumPy is a very popular package, as well as pandas. These are just really great data manipulation packages. So what I'm doing is I'm defining that sigmoid function. So if you remember it from the slides, which you probably don't, and that's okay, it was just this equation. So this numpy dot exponential just means e to the negative x. Then I did not derive this on that PowerPoint slide because it's a very long derivation, surprisingly. But I took the derivative of the sigmoid, and it actually turns out to be quite simple. So I just defined these two functions so we can use them later. Okay, so we've got that part. So we've just got some stuff we'll need later. Okay, so now we're going to create a neural network class. And I just wanted to point out that all of this is here for you, right, to look in later. So, like, here's a link that talks about it. Here's another link about neural networks. Like, there's a lot of stuff here for you to look into later. Okay, here's some Python. Okay, so what I've done is I've created a class called neural network. I'm initializing it. I'm basically saying these are the things that I want in it, myself, the x, and the y. Okay, my x is going to be my features or my training data, and my y is going to be my label or what I think it's going to be. Then, since I'm just going to do a 2-layer neural network, so it's not really deep learning, it's not really shallow learning either, but it's just not so deep. Yeah. Shallow learning is something else, so I originally put shallow learning, and then that was confusing. Okay, so you can see I'm just initializing these weights completely randomly. I need weights for my first layer and my second layer that goes into my output. So I need weights that go from here into here, and from here into here. I don't need weights here because this is my answer. Okay. Oh, and then I just initialize the output. So this is just like an array of zeros that I'll fill in with numbers as I know what they are. So fill in array of zeros, that's the shape of my labels. Does that make sense? Okay, so now we talked about feed forward, and this is where we use our history of working with mx plus b, and we sum it, and then we run it through an activation function that basically turns on or off the switch, and then we get our output for that layer. Okay, so you saw this part already, so you should be okay with it. Now you can see our feed forward. So I put a note here. I'm going to assume bias is 0 just to keep things simple. So that's that b value I talked about in mx plus b. We're just assuming it's 0. So what I'm doing, if I look in the inside, is I'm doing the dot product between my input, so the things that come in, and my weights. If you are not familiar with a dot product and would like a quick reminder. Okay, I saw enough hands. Okay, so basically what a dot product does is it allows you to, so if I have, let's see, if I have a row of data, if I have 2 separate sets of data, basically, let's say that. What I can do with the dot product is to say for each of the first values, multiply them together. Each of the second values, multiply them together. Each of the third values, multiply them together. And then once you've done all that, sum them all the way down. So then you just get one number. Okay. All right, so basically what that allows us to do, if I switch back, just to explain what we did there, is here we're doing that sum of xi times wj. So we're summing the input and the weight. We're multiplying the input and the weight and then summing them down. That's what a dot product basically allows us to do, but with lots more values. Okay, so I'm doing that. So I've done my summing of after multiplying all the weights. And then I'm taking the activation function, in this case, that sigmoid function we defined earlier, and I'm basically switching this on or off, depending on what the values are. And so that's my first layer. Now in my second layer, I'm doing the exact same thing, but my input is now this other layer. Now you can make these much more complicated, but for the purposes of this, I just wanted to keep it as simple as possible. But that's it. So that's my feed forward. And now is where you can learn as much as you want to learn about the derivation that I did not do here today. You can learn about how gradient descent and the chain rule are related to helping us get to the closer to the right answer. So this is the pretty important part. So I definitely recommend reading more about how these things actually work in practice. Okay, so if we take a look at the code, you've seen this part already. We initialize it. Then we do our feed forward. Okay, now we're going to do our weights. So what happens here is we basically find the derivative of the loss. And then we find the derivative of that derivative for the loss. So that's where the math, this is where the math gets very complicated, and I won't get into it today. But the point is we do some math here, And then what we do is I basically say, take whatever those weights were, keep those weights, and add the derivative of the weight, so the change in the loss of those weights. And do this again here. So again, what we're going to do next is we're going to go through and we'll do feed forward, then we'll do back prop, then we'll do feed forward, then we'll do back prop. So we'll go back and forth. Okay. Oh, I got to switch here. Okay. So I run that. See, it's run. Okay. Now I talked about this example, this handwriting example, which I think is really important for you all to check out and work with. Now for today, like I said, I wanted to make it as simple as I could. So instead of using handwritten digits, and instead of using 28 by 28 images that have 784 pixels, I just decided to use Ls. So here I have some images, and basically my goal is to determine does the image have an L in it or not. Okay? So pretty simple. I think you can all see, like this is an L, L, not L, not L, L. So very easy for us to see, right? Now, how do we take this and turn it into something that math or a neural network or Python can understand? So what I did first is I put them into a grid. So you see it's the same thing, I just put them into a grid. And now basically I'm going to roll them out. So like this is my first 3 numbers, this is my second 3 numbers, and this is my third 3 numbers. So image 0 I will represent with 9 numbers. The numbers being 0, 1, 0, 0, 1, 1, 0, 0, 0. Good? Okay. So I can make a grid like this. Now, some of you might be able to stare at this grid and tell me what the pattern is that determines that an L is in an image. Noting that, again, this is an L, and image 4 is an L. So 0, 1, and 4 are Ls. And if you can't pick it out, that's okay too. Anybody see the pattern for what makes an L in a picture? Yeah, go ahead.
1 blue, 2 white, 2 blue?
Yes, so if you have a pattern of 1 blue, 2 white, and then 2 blue, that's going to be an L. So very nice. So here's an L, here's an L, here's an L. Okay, and then here's each of those images represented as numbers. So this should be something that if we can kind of figure it out after staring at it long enough, maybe a computer can figure that out too. So, but that's what the neural network is going to try to determine. What is this pattern that results in an L? Okay, so what I did is I basically took that and turned it into a matrix and added labels to it. So we see this is image 0. A way you could fact check that is this tells us it's an L. So you can see the way it semi does this highlighting where the L's are, and I've also labeled those ones with L's with 1. So there's an L here, there's an L here, there's an L here. Okay, then I said, okay, what are my features, or what's my training data, and what are the labels? So I basically use some Python to split that array. So we can see our features and our labels. So if we think back to our neural network, if I go back, that we initialized, we now have our X and our Y that we'll start with. Okay, where were we? Here. Okay, so now we're basically going to say, okay, initialize that neural network. So this is a class we created through this notebook, and give it the values it needs, so X and Y. So we're going to do that. So now we can refer to that as just in. We're very lazy, so we use a lot of acronyms or things that only we would understand. Makes us feel smart. Anyways, So as my final step, like I said, in the image, we're basically going to feed forward, then go back, then go feed forward, then back prop, then feed forward, then back prop. And what this means is for I in range 1500, so that means for every number in the range of 0 to 1500, go forward, then go back, then go forward, then go back. Okay, so that's all this means. Do the feed forward part, then do the back prop part. Oh my gosh, I said fart. Sorry. So embarrassing. Okay, anyways. So then what I'm doing here is saying, okay, I'm just doing some funky stuff so that it comes out looking nicely. I'm just saying for each value that we want to predict, the two-layer neural network is round what the output is, the output of that neural network, and then multiply it by 100 to make it a percentage. And then I only want to see the first 2 decimal places. So this is just some silly Python that makes it look complicated, but it's really not. So I'm taking the output, making it a percentage, rounding by 2, and saying the two-layer neural network is blank % sure that image 0 or 1 is an L. Okay, so we run that. It's very fast. And I'm able to see that the first image is an L, the second image is an L, and the last image is an L. So it works pretty good, right? I mean, it's a simple problem, relatively. We only had 9 pixels. Usually an image has 784, and a colored image will have at least 3 784s, right? Because it'll have layers of colors. But this is hopefully a way that you can see what's actually happening behind the scenes. Now you can go use libraries from scikit-learn or TensorFlow, and when it does this thing, you're like, oh, I kind of get what they're doing. But you don't have to know all of this to be able to use those things. It's just important that you understand how it works so you know what your answer actually means. Does anyone have questions about this notebook? Yes? Do I have access? No. The way I built this one, I do not. But that would be a great addition to this. So you could see how it was determining the pattern. So I will take that as feedback, and thank you. Other questions about the notebook? Yes, in the back. Why 1,500? We could do less. Do you have a number you want to try? No, I'm just wondering. So I plotted this with a variety of ranges, and I saw that after about 400, it didn't really matter. Like the sum of the squares loss kind of goes to 0 here. So for example, if I change this to 600, I would think we would get, basically the same results. So it's just going to depend on your scenario, some trial and error here. There are some practices behind deciding how many times to iterate through. And especially if you had a more complicated model, this is going to be a more interesting question because it will obviously take longer the more iterations you run. Sure.
So on the 2 that says it's like basically 0% sure that it's an L, is that just because of the way it was coded, or would it be fair to say that it's actually 99% sure it's not an L?
Yes, that. So what he said is right. Is it 0% sure that it is an L, or is it 99% sure that it's not an L? And it is 99% sure that it's not an L. Yeah, good question. Cool. And then here's a reference where you can read about a lot of these steps as well. I think they do a really good job of explaining it. And I also think running through this code and understanding line by line, even this this nasty part would be good to understand. Cool. So let's see. Where are we? Okay, we talked about this. So again, just to compare what we did, this is 784 pixels. We had 9. We were basically saying, is it an L or not? And this is saying, is it a 0, 1, 2, 3, 4, 5, 6, 7, et cetera. So the problems are much more complicated, but this is just the simplest example I could come up with. That's a link for that as well, that notebook we just ran through, so you can run through it yourself. If you download Azure Data Studio and basically open this notebook and try to open a Python thing and you don't have the right version of Python, it'll install it for you. So it's pretty easy to set up this particular demo. OK, so now we've kind of talked about the math. So this was the heaviest part, so you can all kind of like breathe. And we're going to talk about, OK, how can you get to working with these and using these in the future in your lives. Anyone heard of the data science virtual machine? OK, so the data science virtual machine is free in a sense. It runs in Azure. It comes pre-installed with a ton of stuff. So basically, a lot of different software that people use for experimenting. So for example, if you deployed a DSVM and then you open this notebook, you'd have everything you needed already. It also has support for doing things like GPUs or FPGA. I always forget what that acronym is. FPGAs. So if you need more compute, we're able to help you give you that compute, and a lot of the stuff's already in there. There's also a Geo DSVM. So if you're doing stuff related to maps and satellite data, we have like a license that's included in this DSVM. And the only thing you pay for in the DSVM is like paying for a regular VM. So like we give you everything inside it for free. You just have to pay for the VM. So this is kind of my go-to VM when I go create stuff. Now, in Azure, we talked about some of these already. We have our cognitive services. So these are our models that are pre-trained. So you can just start today, start using these APIs, start using these containers that already have models in them. We have support for a lot of these frameworks. One example to call out, Onyx is basically something that allows you to take a model you create anywhere and be able to use it other places. And for example, this morning with Azure SQL Database Edge, we announced public preview, and we also announced the support for Onyx models. So you can actually deploy your models to your edge devices running on, for example, the factory floor, or in automobiles, or in coffee machines, or whatever. Then we have some productive services. So we have things like Databricks, which a lot of you have probably heard of, which basically makes it easy for you to use Spark on top of your data. With big data clusters in SQL Server 2019, we also put Spark and Hadoop in that. So you can basically use T-SQL to access, well, you still write Spark SQL or something, but you can use Spark from within SQL Server 2019 big data clusters. We talked about the data science virtual machines. Azure Machine Learning has made some big advancements on the side of automated machine learning. So basically, it can do a lot of the feature engineering for you, so identifying which features are important and testing out a few different algorithms. And then because you're running in Azure, you can do things like access CPU, GPU, FPGA, whatever you need, only when you need it. So if you're going to train some big model, you can leverage FPGAs, and then when you're done, you're just done with the FPGA, and you don't have to pay the really pretty penny that those things cost. OK, I did want to spend a few minutes talking about how this works in SQL, since this is a SQL conference. So we saw a little bit. I showed you how I was using Java in SQL Server 2019 and Python in SQL Server 2017. R has been available since SQL Server 2016, and R is also available in preview in Azure SQL Database. So you can access some of that there. You can do .NET and do similar sorts of machine learning in CLR. There's a whole language called ML.NET that we author. And that way, if you're using things like managed instance, you could also do that via CLR. But how this works, not for CLR, but for what we call machine learning services and extensibility, is you write T-SQL. And what this does, and I kind of talked about it earlier, is SQL Server then launches these satellite programs. But it's not running in the SQL Server OS, which is important because there were some concerns that, like, hey, if my Python thing blows up or there's some bad actors, then that might affect my SQL Server OS. So we took it completely out, but it still has access to the data, so you can still do in-database machine learning, which means you don't have to ETL that data anywhere to do the machine learning. In 2019, we announced Java, which, like I said, is not really a machine learning language, but you can use it to do other things like leveraging cognitive services or just other things that aren't even related to machine learning, which is why we changed the name to Machine Learning and Extensibility. We're also working on actually opening this up so that if you want to use .NET here, or you want to use, somebody wanted to use F# here, and I said, what's F#? So we're thinking about opening this up so you could actually write your own language extension and then do whatever you want here. And again, this is running on Linux and Windows, and containers has support for this as well. So this is really available on SQL, and one of the key kind of benefits of working with SQL, and I don't know if any of you were in Bob and I's session earlier today, but we're basically saying SQL is everywhere. So regardless of how you want to deal with your machine learning and your neural networks and whatever the intelligence that you're doing in your applications, we're allowing you to basically train and deploy wherever, right? So you can train and deploy in the cloud using Azure services, using Azure SQL, using other Azure services, and then you can take those models and deploy them to your on-prem environment, leveraging things like the R or Python or Onyx support, and you can even deploy those on the edge. So actually earlier today I was trying to figure out what all these icons down at the bottom are, and I'm not really sure. So I think what they're saying is you can deploy them to cars, factories. Any ideas? Fitbit. There you go. Is that really? That's a weird Fitbit. Okay, Fitbit. What would that next one be? Sure. Okay. The chips. I guess you can deploy them to your chips. You can deploy them in your eyes. I got no ideas on the last one. Satellites. Yeah, there you go. So you can deploy them to satellites or drones or whatever. Yeah, sorry. But yeah, basically the idea is SQL is everywhere. Deploy, train, whatever you want. Just leverage the stuff that you're doing. You don't have to move the data in this case. Moving models can be very small. They're just usually binary or serialized. So yeah. Now we have a quiz. Did you guys know there would be a quiz? I really expected everyone would just stand up and be like, thanks. We're out. Okay, so we're gonna have a quiz. I have no prizes. Yeah, I saw some people stand up. So the quiz just keeps getting worse. Actually, I do have some red candies and green candies and yellow as well. No, I'm just joking. Okay, it's late in the day. Okay, who wants to take a stab? What is data science? Yes, it is Wednesday. The analysis of data using scientific process. So we talked about this is the data analysis you already do combined with scientific processes. And I told you about the team data science process, which can help you with the data science life cycles. We also talked about artificial intelligence, which is marketing words. Should we start over? Come on, you guys know what artificial intelligence is. It's a broad category that represents anything that yes, thank you, I appreciate it. That mimics human behavior, so speech, vision, reasoning, etc. Okay, we talked about machine learning, which is making predictions from data, so leveraging algorithms to make predictions from data. we talked about a neural network. Okay, this is the one I'm excited about. Any takers?
Like way to determine whether something's on or off by a lot of inputs. Multi-layered learning system. It's a feedback system that gets closer to.
There you go. I like it. I'll take them all. I just went with common machine learning technique, but you guys are better. Okay, now a deep neural network is a neural network with a lot of hidden layers. Today you didn't really see a deep neural network, but I think you can kind of get the idea. And then Azure and SQL Server can help. So that pop quiz wasn't too bad, right? Okay, so now, reminder about the pathway. So how does this apply to your real life? Well, fortunately, we created a pathway that we thought could apply to most of the people here. The developers, the DBAs, the BI professionals, and the analysts. So I highly recommend, I've taken a look at all these sessions, we've all kind of worked together on them, and they're all awesome. So I think you could spend all day tomorrow doing AI stuff, and then Friday doing AI stuff, but I guess it's a SQL conference, so you might have other things to do. But there are a lot of great sessions here that how you can actually take what you saw today, hopefully you absorb some of it, and start applying it in your job. Not saying you're going to go build neural networks from scratch in the coming days or weeks or months or years or your lifetime, but you can at least start to apply them in whatever situation you're in. And with that, I will end early, and I will take questions. I will say a few things, actually, JK, not ending. Psych, you're still here. Okay, so 2 resources. Okay, and I'll put the link up with those resources. One is SQL workshops. Bob Ward, Buck Woody, and myself have worked really hard on this site. You can learn a lot about SQL Server, so SQL from ground to cloud, 2019. We've also got labs on Azure SQL and migrations. Here's some interesting ones. We've got Python for the data professionals, R for the data professionals. We've got a whole thing on big data clusters and how this relates to machine learning. And then we have a whole thing on machine learning with SQL Server. You can also access all our code and stuff and that sort of thing. Now, the other key resource is my GitHub. I'm very clever. It's analytics with 2 N's. Okay. But what I put in here is all the sessions I do related to SQL. So if you come into SQL Pass, you will see all 3 of those notebooks you saw. Now again, I said for these 2 notebooks, I didn't include all the code, but they're in the greater GitHub, they're in here. So this one's cognitive services, this one's machine learning. So all the resources are here. My slides are here. I am super proactive. I checked in my slides 2 hours ago, so that's when I was done with this deck. But no, I'm just joking. I've been practicing it a long time. Anyways, that is my session. If you have any questions, I will stick around. I won't make all of you stick around. And feel free to email me, tweet me, whatever. I'm available. And thank you so much for staying for this session. I hope it was useful. Have a wonderful rest of the conference.